of Trier for organizing this autumn school. Unfortunately, we are not able to meet each other in person, but the advantage of it is maybe that we can attract more participants to these events and that we can make the results of our research more accessible to all these students around the world who in a normal situation would not be able to travel and come to Germany. So the topic of my talk today, let's call it a tutorial, is related to how can we develop efficient solvers for finding exact solutions for the very difficult bilevel optimization problems that involve discrete variables both at the upper level and at the lower level. So let us start with a short introduction regarding the definition of bilevel optimization and regarding the notation that I'm going to use in this presentation. So in general terms, bilevel optimization is a mathematical tool, modeling tool to model decision-making processes which are done in a hierarchical fashion. In this hierarchical process, we have a decision maker which we call a leader, which makes a decision first by anticipating what will be the reaction of the second decision maker, which comes next, which we sometimes call the follower. In mathematical terms, so what we know is that the leader can anticipate the decisions of the follower because we assume that the leader has a perfect information regarding what is available to the follower, both in terms of the input parameters and in terms of the objective function that the follower wants to optimize. In mathematical terms, this is a most generic way of writing a bilevel optimization problem in a form in which we will say that the leader controls the x variables and partially controls the y variables, because the y variables, they also have to come as the optimal solutions of the nested parametric optimization problem, which is described here in inequality 3. Where we say that y has to be the optimal solution of a problem where x comes as an input, which means the follower observes the reactions of the leader, reacts, and finds the optimal way to maximize or minimize, in this case, the objective function. So in game theoretical terms, you would say the capital F is the payoff of the leader and small f is the payoff of the follower, and each of the players looks into their payoffs and tries to find the best solution. In terms of notation, let n capital X denotes the set of all decision variables, index set of all decision variables in the upper level, ny all this index set of all decision variables of the follower, and the solution y, which is the minimizer of the follower's problem, sometimes I will refer to this solution as the optimal follower's response. Now, in general case, you can imagine that these functions f and g, in the simplest possible case, they could be linear functions or affine functions in both upper and lower level, and that the generic set x and y that I am representing here are simply the sets of all real numbers. In this case, we obtain something that we call LP, bilevel optimization problem, which means both at the upper and at the lower level, we are dealing with linear programs. And you have seen yesterday from Martin a lot of techniques how to solve these problems, and you have also learned that even in this simplest possible case that you can imagine, the problems are strongly NP-hard. Now, of course, you can complicate the things much more, and you can think, okay, what happens if the functions f and g at both levels are nonlinear, but maybe still convex and smooth? Or what happens if the sets x and y also encode some kind of discrete structure? So in my presentation, we will look into the special case in which we stay at the linear, with the linear objective functions and linear constraints. However, there are discrete elements in the sets X and Y, which means that both at the upper level and at the lower level, we may have some integer variables. In that sense, we can say that we can have a mixed integer linear program at the upper level and a mixed integer linear program at the lower level. Okay, so before we go on, let me give you an alternative way of reformulating this bilevel optimization problem using what we call a value function reformulation. So as we said, the solution Y that is a feasible solution for the leader is actually has to be an optimal solution of a parametric optimization problem, which is described like this. And so if I now, for every single choice of X, look into the optimal solution value of the lower level problem, then we define a new function that we call a value function. And by using this notation, now we can reformulate the whole problem as well, the problem that we have here. So basically, in the bilevel optimization problem, what we are concerned with is the optimal decision, the optimal solution for the leader. And so we are minimizing the objective function of the leader. We have to make sure that the solution is feasible for the leader. But now we also add the constraints for C, saying that the solution also has to be feasible for the follower. And finally, the crucial information that the vector Y is the optimal response of the follower is given by the constraints for D. And so these are the value function constraints. So recall that the function phi actually minimizes the objective F. So if we state this constraint like f of xy is less or equal than phi of x, we know that there will be no solution where there is a slack in this inequality. So this will be attained actually with equality, and this constraint will guarantee that the solution y that we receive is the optimal response of the follower. Okay, so now this reformulation suddenly looks a little bit more like a standard single level optimization problem, except that we have, of course, the difficulty that we do not know the value function and we don't know how to describe it. Actually, in bilevel optimization, the value function will be non-convex, non-continuous, and will be very difficult to describe. So this is where the difficulty of the optimization comes from. Nevertheless, most of the approaches will start by dropping these constraints for D and then trying on the fly to approximate these constraints on the way of searching for the optimal solution. So regarding our notation, let us introduce a little bit of terminology. So for a given set of X, we define a separate parametric optimization problem. And the feasible region for the follower is then simply defined by all the constraints g of x, y less or equal than 0, and y and y, and they are denoted by omega of x. What I call the follower's optimal response is also sometimes called in the literature follower's rational reaction set. And again, it is also given for a given x. And this is simply the set of all optimal solutions of the parametric problem defined by the given x. And now the set of all bilevel feasible solutions is actually the set of all points x that are feasible for the leader, well, the points x, y, such that x is feasible for the leader, that constraints at the upper level are satisfied, and also that y is the optimal response of the follower, or that y belongs to the follower's rational reaction set. And so sometimes in the literature, this is also called the inducible region. So I will interchangeably use the terms bilevel feasible set or the inducible region when referring to these points. Okay, now we can simply reformulate the bilevel optimization problem as minimize the objective function of the leader while making sure that you are exploring all bilevel feasible solutions. Okay. Okay, so yesterday you also heard that there could be multiple optimal solutions at the lower level, and that not all of them are equally good for the upper level objective function. So that means that we can talk about optimistic or pessimistic settings when solving bilevel optimization problems. And the difference is that in the optimistic setting, the leader will assume that among the solutions, optimal responses of the follower, we will choose the one which fits best our objective function. In the pessimistic solution, it's the other way around. If you look into this generic problem definition, whether the problem is optimistic or pessimistic can be also hidden in these linking constraints. So you could also use linking constraints to encode the information whether you want to be optimistic or pessimistic. Basically, if you're optimistic, you don't have to do anything. If you're pessimistic, you could hide it here by adding additional constraints stating that among the all optimal solutions here, you want the one that is the worst for your objective. Okay, as we said at the beginning, the information is perfect, at least for the leader. In some papers, you will also read that the information is perfect for both players. It makes no difference because the follower, even if the follower knows that the leader will, what will be the leader's strategy, the follower acts rationally in the sense that the follower maximizes her or his own payoff defined by the given objective function. Okay. And so now we focus on the mixed integer bilevel linear programs. And this is the notation that we are going to use throughout this lecture. So at the follower, at the upper level or at the leader level, we have a linear objective function, which is separated by the decision variables x, which are fully controlled by the leader, and the decision variables y. Then we have constraints that we call the coupling constraints or the linking constraints. And I should mention that just like in the linear case, existence of these coupling constraints, the problem becomes much easier to solve if the GY matrix is zero. And then we will have some subset of variables at the upper level which are imposed to be integer. So not necessarily all of them. So you could say this is a 5a to 5c as a kind of a MILP. And then at the lower level, we have a similar situation. Now at the lower level, the follower is solving a parametric MILP, in which you could also safely put this AX on the right-hand side, because for any given X, this actually becomes a constant. Nevertheless, we have a linear objective function, constraints, and a subset of variables, which are supposed to be integer. Again, in our notation, Jx will be the index set of variables, which are constrained to be integer, and J1 also index set of y variables, which are constrained to be integer. Okay. Just as a reminder from yesterday, already bilevel linear programs are known to be strongly NP-hard. And if you have on the left-hand side, 0,1 ILP, for example, with the constraint that X is supposed to be a binary variable, you can reformulate it as a bilevel linear program in which you replace the condition that X is either 0 or 1 with an optimization problem in which there are no discrete variables. We optimize it in X, and it's an extended formulation, and we add one more dimension, which is the dimension Y. We impose the linking constraint that Y has to be 0, and at the same time, Y has to be the optimal solution of this linear parametric linear program. So this is actually the other way of stating that Y is equal to the minimum of x and 1 minus x. Okay? So if I look at the red line here, the red line here is giving me all optimal solutions when I move x from 0 to 1, then the optimal followers response or optimal y will be here. However, by adding the coupling constraints that y has to be equal to 0, we are at the upper level. We are now discarding all the other solutions and we are keeping only x will be either 0 or 1. So we have this translation. And because we know that the 0-1 LPs are strongly NP-hard, we also see here that, the proofs are given in these two papers, that we know that the problems that we are dealing with now, when we shift from the LP-LP into MILP setting, will be at least as hard as this situation. Okay, so some bad news. Even checking a feasibility for the mixed integer bilevel MILPs is in general strongly NP-complete. So let's see what is the intuition behind this. If I give you a solution, let's say x star, y star, how can I check whether this solution is feasible for the bilevel MILP? So recall, I will use now the value function reformulation, that I can rewrite the problem in this way. So what I have here is a mixed integer linear program plus the value function constraint. So how can I check whether this point is feasible or not? So if I ignore the value function constraint, it will be enough just to plug in the values, and this can be done in polynomial time if I'm given a compact model. However, I have the difficulty that I also have to check whether the value of the solution y star is the optimal response for the leader. And in order to do that, we unfortunately have to solve the followers MILP in order to figure out what is the value function for the given choice x star of the leader. Once we find this value, we simply have to check whether the value that we obtain by plugging in y star satisfies this condition. So simply evaluating phi of x, evaluating the value function for the given x, requires solving an MILP, and therefore, because solving this MILP is strongly NP-hard, then checking the feasibility is NP-hard as well. Okay, so these are bad news. So we cannot expect that the complexity of these problems will be better than this. And in 2014, Andrea Lodi and colleagues, they showed that solving MIBLPs is sigma 2p hard. So now without going into details about the complexity hierarchy, if you just focus on what is the consequence of this result for modeling our problems, the consequence is that it is rather unlikely, unless the polynomial hierarchy collapses, that we will find a way to formulate MIBLP as a MIP of polynomial size. Okay? And so if we think of developing branch and bound algorithms for solving these problems, that means that in every node of the branch and bound tree, we will have to solve another NP-hard problem, at least for checking the feasibility, for calculating phi of x, which will happen at different stages of the branch and bound. Okay, so the way how I have organized the rest of my presentation is as follows. In the first part of this tutorial, I will talk about the way how we can develop a finally convergent branch and bound approach, under which conditions we can do that. I will also show you some difficulties along the way, how that we can have unboundedness and infeasibility issues. And then I will also introduce intersection cuts that will help to speed up the convergence of this basic branch and bound algorithm. In the second part, Then I will talk about further enhancements for branch and cut solvers. And in the third part, we will focus on the special family of bilevel MLPs, which are those that have some kind of interdiction structure. So let's go back to the value function reformulation. So if I now use our notation from before, we could reformulate MIBLP as the following single level problem, where the constraints 8 are the constraints coming from the lower level, together with constraints 12, integrality conditions, and constraints 10 is just a reformulation of the value function. Now, this is the full formulation of the problem. As we said, constraints 10 are the difficult ones. So the first thing that we could do is we could drop off these constraints. If we do that, then clearly we will be relaxing the problem. And in the literature, the name for this specific relaxation is called the high point relaxation of the problem. So this means that for the minimization problems, whenever we solve HPR, we will obtain a valid lower bound for the leader. Now, when you look into the structure of this HPR, contrary to the LP-LP case, now we are still solving a mixed integer linear program, okay? Because some of the variables will be integer. So you can also think of the next relaxation, the simpler one, in which you will drop the integrality constraints. You can do that, of course, now as well. And I will denote it as HPR bar. And that will be simply a linear program obtained by putting together the constraints from the upper and the lower level together and minimizing the objective function of the leader. So clearly, the LP relaxation value will be much smaller than the MILP value obtained by HPR, but nevertheless, there are papers that show that still this HPR value can be arbitrarily bad, arbitrarily far away from the optimal solution value. But not only that, I will show you in a few slides later, that we can have situations in which the HPR value is, that the problem is unbounded, which means that the minimum is minus infinity, and that nevertheless, there is an optimal solution of the bilevel MILP. So this is rather counterintuitive. And I will show you a few more examples where you will see that you cannot easily draw analogy between the standard MILP, or let's say or standard optimization in the mix of discrete continuous variables, and not even you can easily draw a parallel between, for example, two-stage stochastic optimization or two-stage optimization with recourse and the bilevel optimization. There are some turns, there are some counterintuitive elements that you have to keep in mind when developing algorithms for bilevel MIPS. Okay, so let us start developing a little bit of intuition for these problems by looking into an example of Moore and Barth, who were the first one to introduce bilevel optimization with discrete variables. So we have in this example just two decision variables, the variable x controlled from the upper level and the variable y controlled from the lower level. Now they are both imposed to be integer, and there are no constraints at the upper level. The leader just maximizes, if you want, x plus 10y. So we are looking into this direction, something like this. And the follower minimizes the coordinate of y under some linear constraints. So if we draw it, and if we start first by formulating the problem using the high point relaxation, remember what we do is we simply ignore the objective function of the follower, and we plug in all the constraints from the upper and lower level together. And then we obtain something which is a polytope or polyhedron, depending whether it's bound or not. And now we try to find the optimal solution of this problem. So if we do that, so the blue lines here, they show the region, they show the constraints of the follower. And now if you go and maximize x plus 10y, on this problem, the optimal solution that you will get will have the coordinates 2 and 4. So this is this point here. Okay. Accidentally, in this particular case, the optimal solution of the relaxed high point relaxation will be also the same point. However, let us now think what will be the bi-level feasible points for this particular problem. Remember that bi-level feasible points, if we go back to the original problem definition, we have x that has to be integer, so we can only look at x equal 1 to 8. And then for each particular x, we are actually searching for the best follower response. So if we are here and if I fix, for example, x equals 3, then the feasible space of the follower will be the points 1, 2, and 3. However, the best response for the follower is the point 1. So the only bi-level feasible solution where the coordinate x is fixed to 3 is the point y equals 1. And similarly, you will figure out easily that the red points depicted here are actually what I call the inducible region or the set of bi-level feasible points. So the other points, unfortunately, they are part of the high point relaxation, but they are not bi-level feasible. So remember from yesterday, from what Martin told you is, first of all, if we are solving bi-level linear programs, then of course there are no integrality conditions, so HPR bar is equal HPR. What Martin also told you is that in this case, the optimal solution of the bi-level LP will be a vertex of the HPR relaxation. Unfortunately, this is not the case for us. Even if you have a look at the convex hull of the integer points of the HPR relaxation, you will figure out that the optimal bi-level solution lies in this particular example, lies in the interior of this convex hull. Namely, the optimal solution for our bi-level optimization problem will be the point 2, 2. So among these, how many points we have? 8 points. If we evaluate the objective function, we will figure out that for x equals 2 and y equals 2, the objective is minus 22, and this is the optimal solution. So it is not even the vertex point of the convex hull of the HPR relaxation, where we look at the integer coordinates or integrality constraints in the HPR. So this is really a difficulty if you think of convexification methods that could lead to the global optimization search, which means that we will have to deal with disjunctions, which are a little bit more involved than the standard disjunctions that we are used to deal with in the standard MALP branch and bound approaches. Okay, now the next counterintuitive thing about bi-level MALPs is related to the relaxation of integrality constraints. As I already mentioned, if you think of a two-stage optimization problems like two-stage stochastic or robust optimization with recourse, where the recourse is a convex function, then by relaxing the integrality conditions at the first and in the second stage gives you a valid lower bound. Unfortunately, for the bi-level MALPs, this is not the case. So let's stay still with this example and let's see what happens if we relax the conditions and say x and y are both continuous variables. And now we want to solve a bi-level LP-LP. So what happens now is that the set X is a continuous set, that's fine. But now, because we are also relaxing the conditions at the lower level, then the feasible set, for example, remember we said when X is equal 3, then the feasible set of the follower was only points 1, 2, and 3. Now the feasible set of the follower is the whole segment here. And so the optimal response of the follower is this point here, slightly below the point 1, right? It's a fractional value. And so by repeating these arguments, you realize that these two red lines are representing the inducible region or the optimal bilevel feasible solutions in case that we have relaxed the conditions at the upper and at the lower level. So where is the problem now? Remember that the bilevel feasible solutions in the integer case were those 8 points here. Now, what you can see is that by relaxing the integrality constraints, what happens is that the relaxed set, the relaxed inducible region, doesn't even contain the set of bilevel feasible points. Okay, so there could be some intersection. In our case, there is one point which intersects, and it happens to be the optimal solution of this relaxed problem. And so in this example, this point gives us a very upper bound, but you can also create examples where by relaxing these constraints, you get a lower bound. And in theory, there is no guarantee that there will be any kind of relationship between the relaxed problem and the original one. In other words, this is not the right way to go if you want to derive a valid lower bounds for the problem. The right way to go is to work with the high point relaxation. A little bit more of intuition again behind is that if you rewrite the problem using the value function reformulation, our problem here, on one hand, you are relaxing the constraints in the space of X variables because you're allowing more. But on the other hand, the value function reformulation is too constrained because if I use the notion phi r to denote the relaxation of the lower level problem, then this LP relaxation will have a tighter value, a smaller value, and hence I will be over restricting the space of the Y variables at the upper level. So we mix relaxation and over restriction, which is an intuitive way to explain why in such situation it will, the result that we will receive will be neither lower bound nor upper bound, unless you look into some specific situations where you're solving, for example, interdiction problems, and we will come to that later. In this case, for example, if you have a lower level problem where the interaction is very specific and the linking constraints between upper and lower level problems are very specific, then relaxing the lower level problem will give you a valid upper bound. We come to this later. Okay, so now the general idea of most of, let's say, computational methods which are available in the literature so far on the mixed integer bilevel optimization works with the idea of exploiting the HPR relaxation and developing some kind of a branch and bound or branch and cut algorithm to search for the globally optimal solution. The idea is to solve the HPR relaxation, to check the feasibility of the optimal solution, and if this solution is not feasible, to try to get rid of this on the fly. And the two ways are the most standard ways to get rid of this solution. We can do that either by applying some kind of branching, a multi-way branching, or by introducing cutting planes, or by doing both. And so I will explain you in details how to do that. But before that, I want to also show you a little bit, a few more examples of, a few more counterintuitive examples, which are very peculiar and specific for the bilevel MALPs. So first of them is that, as I mentioned earlier, HPR can be unbounded. And the second one is that the optimal solution can be unattainable. So this is an example from Su and Wang's Wang paper from 2014 that shows you that depending on the direction, on the objective function in which you are optimizing the lower level problem, even though the HPR relaxation is unbounded, you can have a bilevel problem for which there exists an optimal solution, for which the bilevel problem is infeasible or indeed unbounded. So here is this example. So it's a problem in which, again, we only have two decision variables, x and y, and we impose both of them to be integer. And so practically at the upper level, we say x can be only 0, 1, or 2. And then at the lower level, we maximize the linear function d times y, imposing that y has to be at least as big as x. Okay? If we formulate now this problem as a high point relaxation, then we take the constraints from the leader and from the follower, and we impose the integrality conditions. So you maximize x plus y has to be greater than x, and x is between 0 and 2. So obviously, the optimal solution of this HPR is plus infinity. So HPR is unbounded. However, depending on this coefficient d at the lower level, it will be the case that the original bilevel problem is infeasible if d is equal 1. Now, why is that? Let's have a closer look into this. If d is equal 1, then we are maximizing y, and y has to be greater or equal than x. So the problem is unbounded, which means that there is no maximizer of this problem. And hence, if there is no y, which maximizes this objective function, then the whole problem is infeasible. Okay? So in other words, if the lower level problem is unbounded, then the bilevel problem is infeasible. Okay? Next example is the following. What if the coefficient d is 0? In this case, all solutions are equally good. So basically the response, the rational response set of the follower in this case is the set of all non-negative integer numbers. Okay? And in this case, of course, if I maximize x plus y, I have the infinity here, and so the bilevel MALP is unbounded. And finally, if d is equal -1, then the optimal solution of this lower level problem is simply y is equal x. And y equals x means if I maximize x plus y, means that I will put x equal 2 and y equal 2, and the optimal solution will be 4. And so there is a unique optimal solution in this case. So this is really an interesting property of bilevel MALPs that you have to keep in mind when developing your models. And the question is, can we deal with that in practical situations or not? One thing that you can safely assume is probably, if you think of modeling the problem from the practical perspective, is you know the meaning of the x and y variables, so probably you can impose some reasonable bounds. So by imposing some reasonable bounds on these variables, you can actually get rid of the situation that the HPR relaxation will be unbounded. Okay. However, there are some other difficulties that we may encounter. And so let's say we assume that we have added some bounds so that we make sure that the HPR relaxation is a bounded set. The set of all feasible points is bounded. The next question is, now, can the optimal solution always be attained, even in this particular case? So if you try to classify the MIBLP problems, you could say we can at least distinguish these four different situations. One is that at the upper level, we have a mixed integer situation and a purely continuous lower level, or that we have purely discrete variables at the upper level and mixed integer lower level, or purely continuous upper level and MILP at the lower level, or the most general one where we have both discrete and continuous variables at both levels. Now, if you think of developing a finitely convergent approach, even if it has to be a complete enumeration, in the case one, if we have a mixed integer upper level and a linear program at the lower level, you have learned yesterday that these problems can be reformulated as MILPs, okay? And assuming that we can also find the right big M constants and do the linearization, we are sure that, that we will find the optimal solutions by solving the MILP. Okay. Now, if at the upper level, I only have the discrete variables, and at the lower level, we are solving an MILP, then, and I will show you this in a few slides, then it's practically enough that in the brute force sense, because the variables are bounded, you enumerate all possible choices of the values at the upper level, and then for each fixed upper level, you solve the follower subproblem and you evaluate the solution of the leader. And then by just enumerating all of them, you know that in a finite number of steps, even though exponential, and in each of them you have to solve an NP-hard problem, but in a finite number of steps, you will be able to find the optimal solution. However, the situation is much trickier if we have continuous variables at the upper level, and in particular, if these continuous variables are controlling the decisions of the lower level. What I want to say is, if there is a linking variable, the variable in the function phi of x, which is a continuous variable, then unfortunately, we cannot guarantee that the optimal solution value can be attained. And so let me show you what it means. Here is an example from Matthias Kuppe and colleagues from the paper in 2010, which nicely illustrates this situation. And you can also find a bit more involved example in another paper from '96 from Luis Vicente and colleagues. So here is a simple, again, problem with just two variables, x and y. X is a continuous variable from the upper level that controls the lower level. You want to find the minimum of x minus y, and the optimal solution of the lower level is simply stating that y has to be greater or equal than x, y is between 0 and 1, and you minimize y, okay? So if we try to graphically represent the solutions of this problem, this is what happens. When x is equal 1, the optimal follower's response, y is equal 1. When x is 0, 5, because y is greater or equal than x, the optimal follower's response is again 1. And so what happens here is that the red line here is showing you the inducible region for this bilevel optimization problem. Remember, y is greater or equal than x, but y has to be integer. So when x is 0.5, y is 1. Okay? So what we have here is that when x is 0, y is also 0. So this inducible region is an open set, unfortunately, which means that when I minimize x minus y, in the infimum, we will get 0 minus 1. So infimum will be minus 1, but unfortunately, this solution will never be attained. Okay? And so this difficulty comes from the fact that continuous variables in the leader control the solutions of the follower. And so to guarantee the finite termination, unless we want to work on develop algorithms that guarantee only the epsilon convergence up to a certain precision epsilon. So to guarantee the finite termination, a lot of algorithms, and in particular in my presentation, I will also assume that only the integer variables, only the discrete variables from the leaders are the ones that define the value function. And I will denote them as JF, being a subset of the discrete variables from the leader. These are the variables that control the follower, the linking variables. Okay, so now we are ready to develop a finitely convergent branch and bound algorithm based on these assumptions. So what are the assumptions that we will need? First of all, that the LP relaxation of HBR is a bounded polyhedron. And as I said, from the practical perspective, this is probably not very critical because you understand your problem, you can introduce reasonable bounds on the variables. Assumption 2 is really a critical assumption, which says that the continuous variables from the leader do not appear in the follower problem. Now, of course, there will be many applications where you cannot avoid that. Well, in that case, I would say you cannot hope to get the globally optimal solution, but you can still work on getting an epsilon convergent solution. Okay, and the assumption number 3 is that for any x, the follower subproblem is well defined and has a finite optimal solution. This assumption is not too critical because you can integrate it in your branch and bound method. I'm just adding this assumption for the simplicity of the presentation. In any case, for example, if the follower subproblem is unbounded, this can be detected in a pre-processing step by solving a simple linear problem, so we can skip this discussion for the moment. Okay, so now, if I have this situation in which the leader variables, which are continuous, do not appear in the follower problem, and so and in addition, I know that the linking variables, which are integer, can take only a bound from the bounded interval, then I could think of a brute force approach, which would be a very naive approach, but which could guarantee to find the optimal solution. The idea would be that I try all possible combinations of the discrete variables from the set JF, okay? From the variables that define the value function, okay? So this is a finite but exponential set, that's fine. And then I choose the best one, the one that gives me the best solution for the leader. How would that work? So imagine that I take a particular vector, x star, of these discrete variables with this particular choice of the values. First thing that I do is I find the optimal value of the lower level problem, phi of x star. This, of course, requires solving one MILP, as we have seen from the beginning. And once I have this solution, then I have to solve another MILP. And this other MILP is the problem 13a to 13e. In this MILP, I am practically solving my problem, but now knowing that the coordinates from JF are fixed to X star, and also knowing what is the optimal response value from the lower level problem. So if I do that, then remember these are all inner functions plus the integrality constraints hidden in X and Y, we are solving another MILP. And so by doing that, we have an optimal solution for the leader in which all the coordinates from the set JF were fixed to the X star. And now, by making different choices of X star and enumerating all of them in a finite number of steps, in each step I have to solve these two MILPs, I will be able to find the optimal solution. So, as I said, in practice, this is not something that you would prefer to do because this is an explicit enumeration. And instead of that, we can, from the theoretical point of view, we could exploit this, but of course, embed it in a more sophisticated branch and bound approach, because we know that we have HPR relaxation, and we know that HPR itself is a MILP, which means that likely, if we start with the HPR relaxation and do cutting and branching, we will save a lot of unnecessary enumerations of these points. And so this is the idea of the basic branch and bound approach that I will show you in the next slides. So recall that in this setting, we allow both upper and lower level to contain continuous variables. Also that at the lower level, you have a full LP. So the only serious restriction that we have in this case is that the function phi of X, that these variables X here are discrete variables. This is the link. And this is the key point for this branch and bound to work properly. Okay, so general idea of developing different kind of branch and bound methods in the literature is indeed based on this concept of solving the HPR relaxation first and enforcing the value function constraints on the fly by branching and cutting. If we solve the HPR relaxation, for example, in the LP form, and if we obtain a fractional solution, then we can rely on the standard MILP techniques and do the branching and cutting as usual, also using the general purpose cutting planes and standard branching strategies. If the solution that we get is feasible for HPR in the sense that it also satisfies the integrality conditions, and if the solution Y star corresponds to the best response of the follower, which means the value function constraint is satisfied, then this is a feasible incumbent solution. This is a feasible bilevel solution and we can keep it. However, if we have an HPR point, which means it satisfies integrality conditions, but it violates the value function constraint, this means that this point is not bilevel feasible and we have to do something. And what we can do is we could try to generate a valid inequality that will cut off this point. And this has been done in the PhD thesis of De Negre, also in his paper with Ted Ralphs, and also in the recent publication from 2020 that just appeared in the Mathematical Programming Computations, where the authors develop an open source software called MIPS that uses a branch and cut procedure with several types of valid inequalities that can be used to cut off this point. And this idea is also used in our papers that we have published in the last 2 years on developing intersection cuts for cutting off these infeasible points. Other way how you could deal with this particular situation would be that you try to use some kind of the approximation of the value function that you want to improve. And this idea has been exploited in the papers by Lozano and Smith in operations research, and Cleniati and Agiman, who actually developed an approach for mixed integer nonlinear bilevel optimization, in which they call it branch and sandwich, in which they try to provide a valid upper and lower estimation of the value function and to tighten this approximation during the branching process. And finally, another way how you can get rid of this bilevel infeasible point would be to think of applying some kind of branching or multi-branching. And this has been exploited in the Xu PhD thesis and also in their two papers, one from 2017, in which they develop an algorithm which is called a watermelon algorithm. I will show you later some examples. And also another simpler multi-branching idea from the Computers and OR paper in 2014. Also, this specific branching has been exploited in one of the first papers on the topic, and also in the paper of mathematical programming. And I will show you this particular branch and bound now on the next slide. So as I said, this is a simplified version, simplified pseudocode of the branch and bound procedure that we have presented in a MathProc paper. Simplified because I'm now assuming that the follower problem is well defined, that the HPR is not unbounded, so that we can focus on the core of this algorithm. So what is the idea? The idea is that we are solving the HPR relaxation first, and then we try to apply disjunctions based on the branching decisions within the HPR relaxation, and we are collecting the best incumbent solutions on the fly. So until we find a corner point, a vertex of the HPR relaxation, which is not integer, which doesn't satisfy integrality conditions, we can rely on the standard branching and cutting strategies, which are embedded in the standard general purpose solvers, like Cplex or Gurobi. What we have to do is we have to inhibit incumbent update, because for the evaluation of the incumbent, we have to do two things. One is to calculate the followers semi-ALP, and the other one, remember from the brute force approach, is also to apply what we call refined HPR relaxation. So for each node of the branch and bound tree, where standard branching cannot be performed, and what does it mean that the standard branching cannot be performed? That means that all integrality conditions which are embedded in the HPR are already satisfied, okay? So in the simplest case, if we just have discrete variables, this means that we have an integer point, which is the vertex of the HPR that we are dealing right now with. So let's this point be called X star and Y star. First, we have to evaluate what is the optimal follower's response for the given X star. And if the value of X is really, if Y star is really the minimizer for the given X, then this is a feasible bilevel solution. And we can update the current incumbent value and we can fathom the node. So this is fine. The problem is, what if this point is not feasible? What can we do next? And this is now the difference, because remember, in the example of the Moore and Bart, we have seen that the optimal bilevel solution was inside of the convex hull of HPR points. This means that we have to continue branching, even if the point that we have found is integer. So if not all variables that control the leader are fixed by branching, at this stage, the point is infeasible doesn't mean that that inside of the polyhedron there will not be another feasible point, so we have to continue branching. And otherwise, if all the coordinates of X have been fixed by branching, then we have to solve the refined HPR to find what will be the optimal solution value for the leader. Remember the refined HPR, this is this problem here. So we fix the coordinates of X, they are fixed by branching, and then we can evaluate the whole solution. So this is the finitely convergent branch and bound approach, which benefits a lot from the existing procedures which are already embedded in the general purpose MIP solvers. Okay, and for this, it will work fine for the bilevel MILPs at both upper and lower levels, as long as we said, this set JF, which are the variables that control the follower, are actually all discrete. And you don't need intersection cuts. You don't need any additional cuts. You have a branch and bound that works. Now, the idea that we have exploited in the recent papers with Matteo Fischetti, Michele Monaci, and Marco Sinel was, let's now look into this branch and bound approach and try to enhance it by avoiding to branch too much, because of course there is a trade-off between the size of the branching tree and the cutting planes that you're adding and tightening the formulation. And so this is precisely at this place here, after this else, and before deciding to go on for branching, that you would like to try to cut off this point, the infeasible point, X star, Y star, by adding additional valid inequalities. And one possible way to cut off these bilevel infeasible points was to use intersection cuts. And so if you start with this basic branch and bound and add separation of intersection cuts in this step here, then you get a branch and cut approach that I will present you next. Okay. So intersection cuts that have been introduced in the 70s by Egon Balázs are a powerful tool for solving MILPs. And in our recent work, we thought that maybe we could also exploit them in the context of bilevel optimization to get rid of bilevel infeasible points on the fly while solving the LP-HPR relaxation. And so intuitively, if I say that, let us say that this inducible region, which means the bilevel feasible points, are represented by these red points here, and that we have another point, X star, Y star, and don't forget, if we solve the HPR relaxation, and for simplicity, let's say we deal only with discrete variables, this point will be also a discrete point. We have integer coordinates. Now the question would be how to derive a cut that will make sure that when we add it to the current formulation, the infeasible point is on one side of the hyperplane and all bilevel feasible points, or let's say those that are improving, that those that improve the objective function are on the other side. And for the intersection cut, what you need is a cone which is pointed at the infeasible point. And this cone has to contain all feasible solutions inside, okay? And the natural choice for taking this cone would be a cone that you obtain from the LP relaxation, from the LP basis, okay? On the other hand, you also need a convex set which does not contain feasible solutions. And we will call it the bilevel free set, such that the infeasible point is in this convex set, but no feasible points are inside. And if we have this situation, then the intersection cut, that's why his name, will be found as a hyperplane at the intersection of this cone and the convex set, okay? And clearly this cut will separate the infeasible point from the bilevel feasible ones. Okay, so first question is LP basis, but we are dealing with an integer point. How is this possible? Well, this is possible if we run a branch and bound based algorithm in which each point in the branch and bound is obtained by using the simplex method, okay? And if it happens, that's why we say that as long as the solution that we obtain in the branching nodes is not discrete, doesn't satisfy the integrality conditions, we will apply the standard branching and cutting procedures. At some point in the branch and bound tree, we will encounter a point found by the simplex algorithm which satisfies these integrality conditions. So we will be able to have the LP basis and the cone defined by this point. More difficult question would be now how to determine the convex set S which does not contain bilevel feasible points. Okay? And one rather intuitive way to think of this convex set is by looking into the follower subproblem. And here is this intuitive result. Remember, we have the constraints at the follower level, which are describing, let's say, the feasible space of the follower, like AX plus BY less or equal than B. Now, if I take a feasible solution from the follower, let's call it Y hat. And if I plug it into these constraints, the solution is feasible, all these constraints have to be satisfied. However, remember that for the bilevel solution to be feasible, the optimum of the follower has to be considered, which means that any other point Y, such that the objective function value is greater than the objective function value evaluated in the point Y hat, will be an infeasible point. Why? We are minimizing. So everything which is greater than this value certainly is not going to be a minimizer. So that's why we can safely conclude that the set here, which is clearly convex because it's a combination of linear inequalities, that this set doesn't contain any bilevel feasible point. Now the problem is that we don't want this set S, if I'm here, I don't want this set S to contain bilevel feasible point on its frontier, because in that case, the intersection cut is not guaranteed to cut away this point. And in order to guarantee that this doesn't happen in the practical situation, we need to enlarge this set, and we enlarge it under one specific assumption by adding +1 on the other hand, on the other side, on the right-hand side. Now, in order to be able to do that, to shift the coefficients of the right-hand side by 1, of course, these values here have to be assumed to be integer. And so this is an additional assumption in the branch and bound algorithm that we impose, that the coefficients of these constraints at a lower level, let's say that these values have to be integer. If they are not integer, if you can find the small epsilon that guarantees you that if you look at the rational values and if you can find the smallest epsilon to shift it, that is still fine. Okay? So now we will work with this set and we will say, okay, the point Y hat is a feasible solution from the follower for a given X, for example. Now I can define this polyhedron. I have the current solution of the linear program. I have this polyhedron, so I can derive the cut and get rid of this point. This is one possible way to derive intersection cuts. And let's have a look at the graphical illustration to get a little bit more of intuition what is going on here. So we go back to our example from the beginning. And if we solve the problem as a high point relaxation, so remember, the only bilevel feasible points are the red ones, and the feasible points of the HPR relaxations are the red plus blue. Okay, so if we solve the HPR relaxation, the optimal solution is the point with coordinates 2 and 4. And this is also the solution that you obtain by solving the simplex algorithm on it. okay? So we get an LP cone here, and we could take the y hat to be equal to 2. So the y hat equal to, so obviously the point x star, y star with coordinates 2 and 4 is not feasible. It's not bilevel feasible. Why? Because when I plug in and calculate the optimal response of the follower, phi of x, for x equal 2, I get that the optimal response is 2. So this is the bilevel feasible point when coordinate of x is fixed. So if we take y hat equal 2, then the set S looks like this, okay? So everything which is greater or equal than 2 for the given value of x, these coordinates here, is cut off, and the next intersection cut that we get is cutting a significant part away from the HPR relaxation. Now we could continue. Now we solve the HPR relaxation again. Again, we will get a point with integer coordinates, 6 and 2. This is this point. This is the LP cone. Again, this point is bilevel infeasible because the best response is 6, 1. And so if I take y hat equal 1, then the set x, when you calculate it, when you plug it in, you get something like that, and you get the next intersection cut. Okay? So you cut away this point, and after that, by solving the next relaxation, you're lucky, you're here, and you get the optimal solution. So that's the idea of running the intersection cuts on top of the solving the standard branch and bound with HPR relaxation. Okay, so the first question is, how do we find this set S, this bilevel free convex set? And indeed, the very natural choice, and the choice that we have used in this example was, what did we do? You find the optimal HPR solution, then we fix the coordinates x, and we find what is the best follower's response. And indeed, we were plugging in this y hat as the best value of the optimal solution value of the optimal solution of the follower, and we were defining the set S in this way. So this is exactly what we will be doing. If the point x star y star is infeasible, first we calculate what is the phi of x. While we are solving this lower level problem for the given choice of the leader, we are solving the MILP, and we will also find one optimal solution, y hat. And so clearly, the set S star has to satisfy all the points for which the objective value is greater or equal than dt y hat are going to be infeasible. And so we have the choice of the set S plus y hat. Okay? So what does it mean for the separation? Obviously, that means that in each time you have to get rid of this bilevel infeasible point, you have to solve an MILP, which means you have to solve an NP-hard problem. Okay. And so some first insights about how useful this could be are given in this short computational study that I'm going to show you before we close the morning session. So in this study, we took several instances from the literature, randomly generated instances with integer variables that have been proposed in the thesis by De Negre, interdiction instances with binary variables, and the instances that we have derived from the MIP-LIB free zero, also with binary decision variables. And what we tested are the three different settings. One setting in which we have this branch and bound, basic branch and bound approach, and we use the intersection cuts only to tighten the formulation. One option was to tighten the formulation and to add up to 20 cuts at the root node and at every other node, or to tighten the formulation only at the root node. And we also implemented our own implementation just to make sure that we are not depending on the different platforms, because De Negre has proposed a kind of no-good cuts for cutting off bilevel infeasible solutions based on the integrality condition. That's why we have here no continuous variables, because their approach works only for the integer decision variables. But we also implemented it using Cplex solver and the Cplex callbacks to make sure that we work on the same platform and on the same settings. Okay, so what you can see here, let me skip this table and let me just show you the performance profile, is the following. So the benchmark manages to solve 40%, roughly 40% of the tested instances within the given time limit. And these two, our branch and bound approach, in which we separate intersection cuts instead of the cuts proposed by De Negre and Ted Ralphs, solves a little bit more instances, slightly more than 60% of them. What you can also see is that there is a portion of instances which are easy, in which case only tightening the intersection cuts at the root node is sufficient to find the optimal solution. However, then there are some more difficult instances where it pays off also to add the intersection cuts deeper in the branch and bound tree. Okay, so I think this is a good moment now to, even though we are a little bit, we have 5 more minutes, let me just give you now an overview of what we are going to see in the second half of this tutorial. What we have seen so far is the enhancement of a branch and bound procedure in which we use a simplex-based branch and cut approach, and we enforce the value function constraints on the fly by adding cutting planes. We do that to tighten the formulation and to simply avoid branching too much, okay? And I will show you later in the afternoon additional ways of deriving intersection cuts and a way to separate them, and also some tricks on how you could pre-process the follower subproblem and try to fix some of the variables from the lower level problem and add them into the upper level, which can have a significant impact. And I think that these ideas in principle can be applied also for the bilevel inner programs in general, and also the follower upper bound cuts, the local cuts that you can add while branching on the tree based on the current bounds imposed on the upper level variables. Okay, so if this is fine, Martin, if I have the permission, I think this is a good moment to make a break, and then maybe in the afternoon, if I need 5 or 10 minutes more, maybe I can steal them.
Yes, of course you have the permission. Thank you very much for this really fantastic tutorial.